Hello everyone, I'm Zeyi, and I am excited to introduce our work, Unified Near and Far Object Reconstruction via Homogeneous Gaussian Splatting. 3D Gaussian splatting has emerged recently as a powerful approach for novel view synthesis. It achieves high-quality rendering by adopting 3D Gaussian primitives, which provide an explicit representation of the scene. Training is efficient because 3D.GS avoids the use of neural networks, and the rasterization-based rendering of Gaussians allow real-time rendering performance. As shown here, the 3D.GS pipeline begins with multi-view images, camera poses, and an initial point cloud. This point cloud is optimized into 3D Gaussians, which can then be rendered into realistic novel views. On the other hand, 3D.GS struggles in certain cases. There are challenges in representing distant geometry accurately. We can often observe background inconsistency in such areas, especially for novel views, and leading to unfaithful rendering. As a result, the overall quality degrades when modeling unbounded scenes. Why does 3D.GS struggle with distant objects? Consider that we are reconstructing a target Gaussian that is far from the camera and large in 3D space, and we are starting with a 3D Gaussian that is much closer to the origin. To match the distant target, we move the Gaussian away from the origin and adjust its scale to keep it visible at the same time. Even if the scale is updated as the Gaussian means increase, the projected size still changes nonlinearly due to perspective projection. The mean and the scale must coordinate well to maintain a consistent appearance. However, it is hard because they are optimized independently. Furthermore, to optimize for a target that is very far and very large, the Cartesian means and scales will theoretically take infinite steps to reach the target. This makes convergence very difficult for unbounded things. It is hard for 3D Gaussians to be optimized for these distant objects while remaining spatially stable and visually significant at a large distance. The limitation of Cartesian coordinates reminds us the concept of homogeneous coordinates, which extends Cartesian into a four-dimensional space and allows for a more flexible representation of geometric translation. Let the point P in 3D Cartesian coordinates be represented in projective space as P tilde. The fourth element W is called the weight. Although not necessarily related to the distance, the scaling by the weight W in homogeneous coordinates accounts for depth, ensuring further points appear smaller and respecting the real-world perspective. It can also naturally represent the vanishing points and lines in perspective views, which is a fundamental concept in projective geometry. Here's a toy experiment demonstrating homogeneous coordinates effectiveness by comparing the convergence behaviors to various targets in a 1D space. It turns out that for a relatively near target, both representations are close in performance. However, in other cases, the homogeneous representation is able to converge at a faster speed. Inspired by the advantages of homogeneous coordinates in handling perspective projection, we propose our solution, Homogeneous Gaussian Splatting. We want to leverage homogeneous coordinates' ability to seamlessly represent points, regardless of their distance, so that we can improve the reconstruction quality for distant regions, while preserving the high quality for the near ones. We reparameterize both the means mu and scales s of 3D Gaussians into mu tilde and s tilde, which share the same homogeneous component w. By doing so, we ensure that the means and scales act as a unified representation within the same projective plane in order to respect projective geometry. This approach simplifies the optimization of the means and scales for distant objects, which are often not faithfully represented in the original 3D Gaussian. Here we present a visual comparison with 3D.GS. We can see that our method is impressive in reconstructing distant details in the background, preserving both geometric accuracy and detail clarity. Such details are often missing in 3D.GS results. Furthermore, in most cases, our method preserves a comparable level of detail for objects that are close to the view as in 3D.GS. In conclusion, our work introduces homogeneous coordinates for means and scales into 3D Gaussian splatting, and it handles both near and far objects robustly. Our method achieved state-of-the-art novel view synthesis performance at real time, and is effective compared to both implicit and explicit baselines. For more detail, please refer to our project page. Thank you for your time.